So in this talk I'm going to show you how to use these new exciting features of TensorFlow tool that are AutoGraph and tf.function. And in practice this is a tutorial on how to correctly write functions that can be graph converted. But first, a brief introduction about myself. So this is me. I am a computer engineer. I am the head of machine learning and computer vision at Tech Italy. This is a spin-off of a toy company, but we do something completely different. We do houses. And I'm also a machine learning Google developer expert because I'm kind of like obsessed with TensorFlow. And as you can see in the links here, I have a blog in which I write mainly about TensorFlow and the new features of TensorFlow. I have a GitHub where I do a lot of open source stuff, always related to machine learning and TensorFlow. Okay, you can find my spam on Twitter, and I'm also an author of a book, and I will talk about this book at the very end of the tutorial. But okay, after this introduction, we can start. So, AutoGraph and DataFlow graph. So, in TensorFlow 2.0, the old way of executing the computation changed. First, there was a descriptive way of programming, because I mean, the original way of TensorFlow 1 of executing the computation was to use TensorFlow like a descriptive language. A descriptive language in which you first describe the computation, then you take this computation, describe it as a graph, you put it inside a session, and then once the description of the computation is placed inside a session, you execute it, and you are executing a graph. In TensorFlow 2, the graph description plus section execution paradigm has disappeared, or better, it has been hidden, but in favor of the eager execution. Eager execution is the execution of the computation line by line, exactly like we are used to do in Python. But of course, now we can use TensorFlow like NumPy, so line by line, and every time we type a command, this command is directly executed. But TensorFlow, it is designed to run on data centers, and we need to keep all the advantages that having a graph description of the computation give to us. For instance, graphs are speed to execute, because of course you are creating a graph and then you are creating this blob, this description of the computation that you can easily replicate on many different machines and on many different GPUs. And of course, because you can do this because graphs are a language agnostic representation. Because you can use Python to create a graph, but then this graph is not related to Python. You can load a graph inside a C++ application and use it. And of course, automatic differentiation comes almost for free when we are using the graphs to describe the computation. So, in order to bridge the two words of the section execution and the eager execution, the TensorFlow developers introduced tf.function and AutoGraph. So tf.function is a decorator that you can use to decorate your functions that you want to convert in this optimizer representation. The optimizer representation of code, of course, is a graph representation of your function. Internally, tf.function uses another module that is AutoGraph. AutoGraph is a module that allows to convert automatically a subset of the vector language to its graph representation. For instance, if you're used to work with the TensorFlow 1, you know that to create an if statement, you have to do a tf.cond condition and then the two branches. If you are used to do some sequential execution in tf.1, you have, in tf1, you have to use tf control dependencies to force the order of execution of the statements. Instead, when AutoGraph comes in, it allows to use a function written in eager mode and then automatically build the graph for you. So, we can see what happens in practice when we apply this decorator to a function. what happens is that we create a new context. In this new context, the eager execution is disabled. And then on the first call, we have two things that go on in parallel. The first one is the execution of the function as is and the tracing of the execution. So we are observing what's going on when the function in eager mode is executed for the first time. But at the same time, there's the AutoGraph module that comes in and starts converting the if statement, the for statement, the assert, the while loops, and so on to the respective tf dot operation that corresponds to the statement in Python. Then we merge these two parts and we created the graph, the old and lovely tf.graph representation. Then what happens is that we created a graph starting from a certain function that has a certain signature, and then using this function converted and the signature of the function, so the function name plus its signature, we create a cache. In this cache, it's just a map in which the key is the function name and a concatenation of the arguments. And so we just create this association between the function name, the arguments, and the graph representation. Then, on every non-first call, what happens is that we already have the function name and the arguments, and therefore we can just access to the map we created and fetch the graph and then execute the graph directly. Okay, so we can start by solving a simple problem. The problem is we have two constant matrices, so A and X, and we have a scalar variable. And our goal is just to compute the matrix multiplication and summing this variable. In TensorFlow 1, this is what we do. I explicitly show the graph. In practice, there's no need to do this because in TensorFlow 1 there's always a graph, a default graph in the current session. But however, what happens is that a graph is created. We declare using the operations from the TensorFlow package two constants, our A and our X matrices, and then we declare the B variable. Of course, we have to declare the node of the matrix multiplication between A and X, the operation of the scalar addition, and then something that people that are familiar with TensorFlow 1 are used to look everywhere to see often, is the tf global variables initializers, because we have first described a graph computation and we have to execute this computation next in a session. Of course, one of the execution we need to run the computation is the initialization of the variables. So we can just create a session, run the init operation first to initialize the constant and the variable, and then use the session.run to fetch the result. Moving on, we can convert the same code in TensorFlow 2. We have to define the same code in a function, because function right now are the replacement for the sessions, so just logically. But what we need to do is to just keep the previous graph definition and put it inside a function. So we have our def, the A and X constant definition, the B variable definition, and the matrix multiplication and the sum of the scalar term, and then we return the variable. This is an eager mode, there's no tf function decoration, and what we have here is that we can run as many times as we want this function and we get the correct result. For instance, there's a for loop with 14 times the execution. We fetch the numpy value and we can just see the result of the matrix multiplication in the sum. Of course, we have to fetch the numpy value because we are still using TensorFlow, and every operation, for instance, the tf.mul produces a tf tensor that is an object, and to fetch the correct numpy value, we have to use the numpy method to fetch the correct value. Okay. So our goal is to convert this function to its graph representation using tf function and AutoGraph. So we can just think about, okay, we have a function that works in eager mode, we just put a decorator on top of it and we see if it works. I added two statements, The first one is a print, Python print, in which I just print the value of y. The second statement is tf print, so the TensorFlow print, in which I print the value of y2. So, if we remember from the previous graph representation of what happens when a tf function is used, we should see that during the tracing phase, we should see only the first print statement, the Python print statement, and when instead the graph is executed, that print statement should be discarded, and we should only see the tf print output. Of course, we can try to move on. So we have a function that works in eager mode, and we decorated it, and we try to execute it. So this is what happens. Happens that this is the first output, the first line of the output, and this is the print, the Python print, and as you can see, this is a tensor. So this is a tensor, but this is not a tensor with a value inside. This is a tensor of TensorFlow 1, because as you can see, we have only the name of the tensor and we have only the shape, but we don't have the value, the numpy value, because of course eager execution is disabled and we are building the graph. So we are in the tracing phase. Then this is the second output. Perfect. We have this amazing exception that says tf function decorated function try to create variables on non-first call. Okay, to keep this short, we call it the function only once, so this error is a little bit misleading. But what happens in practice is that tf function under the hood can trace the function more than once. So tracing the function more than once means to execute the function and try to create the graph representation more than once in order to spot if the function creates a state. If the function creates a state, it means that the function is creating something like a tf variable inside. And this can be a problem. So, in fact, it can be a problem because a tf variable object in eager mode is just a Python object that gets destroyed as soon as it goes out of the scope. That's why, when we were using the same function in eager mode, we could run the same function 10 times and it was corrected because tf variable was created once during the call and then it gets destroyed at the end of the call. But, when we decorated the function using tf function, a tf variable object is the definition of a persistent node in a graph, and we can't define a persistent node more than once, because of course otherwise we are just creating other nodes, but we want to use the same node because it's the same variable. So this is the solution. The solution is to break the function. So take care of the variable's definition manually. So what we can do is to define use an object-oriented approach. We can define our variables in the init of the function to none. Then we can define the call. This is, of course, when the function gets called. We have our definition of the constant nodes, but a special treatment for the variable. So when self-b is none, we do the first and only definition of the variable object. In this way, everything goes as we expect. So, this is the lesson number 2. That means eager functions are not graph convertible as they are. So, because there is no one-to-one match between the eager execution and the graph built by tf function, of course. So, when we are defining a function that we want to accelerate, we have to keep in mind that we can't just keep a function that works in eager mode and apply the tf function decorator, but we have to think about the graph conversion process. Okay, this is another test. The test is what happens when we change the input type of a tf function decorated function. So, why we have to do this kind of test? Because of course, Python is a dynamically typed language. For instance, we can define a function that accepts a parameter with a certain that accepts a parameter. It can be a string, it can be an integer, it can be everything. In TensorFlow, under the hood is a C++ library, and being a C++ library, it needs to have a correct and strict representation of the types. And of course, the TensorFlow Python library, and in particular tf.function, should bridge these two words. So, as we see, there are some peculiarities to keep in mind when defining a function. So this is the function we are going to implement. As you can see, it's just a function that keeps a parameter x and returns the same parameter x. So this is the identity function with, of course, the two statements for the debugging of the Python execution and of the graph-only execution. So the Python execution is the first print and the graph-only execution is the second tf print. Let's see what happens when we use a tf tensor as input. So this is the first test. We just define a tf tensor using the tf constant code of type float32. We call it once. Then we just define another tensor with the same type. We do the second call with a different value. And we do the same test with the unsigned integer with the 8-bit. And we do the same thing. Let's see what happens. Okay, on the first call we have the tracing and graph creation. So we expect to see the Python execution once, then the graph execution, because okay, we created the graph and then we are executing the graph. On the second call, we don't have the Python execution, but we have only the graph execution because we are reusing the graph. Okay, it works. The second test happens the same type. It happens the same stuff. So on the first call with a different type, first we are going to create a function, a graph. So first we are going to use to trace the function execution, and then we create the graph. On the second call we are reusing the graph. So it works as we expect. So since everything works as we expect, we can start to have a look at what's going on when we are converting the function to its graph representation. We can use the tf.AutoGraph module that allow us to convert to code, so machine-generated code that is difficult to read, but of course we can read it, the Python function. So this is the output, and as you can see, this is our function that we expect. So to accept all the parameter x and return a certain parameter that must be x. But of course, there are something that is strange here, because of course we have created a function and we are creating a graph. We expect that our graph only contains the graph-convertible part, so we expect to have an input, the tf print, and the return. But instead, here we have this call, and this call is a call of a Python function, our first print statement invocation. We can look at it in a better way, so formatting it. So what happens here is that although it is only a Python code, even in the graph converted code we have a reference to the Python code we have executed. But of course, as you can see here, the AutoGraph converted code have a second parameter that is none. When the second parameter is none, this is the owner of the statement we are invoking, so of the function of the statement we are invoking. So when it's none, just means that all this statement becomes a TensorFlow on operation. So it basically just does nothing, this line, but is needed because AutoGraph needs to force the order of execution, and the most important part of this code block is the control dependency at the beginning. Because of course, since in Python we declared the function Python, mixed Python and mixed TF only operations, we want to replicate the same behavior even in the graph mode. Of course, AutoGraph should try to emulate in the best possible way this behavior, and so we have these operations that are basically no operation but force at least the execution of the correct. We can move on and we can see what happens when there are Python native types as input, so no more TF tensors but Python native types. I defined a simple function, print info, that just print the info of the input. So we have the type and the value. And we executed some tests. The first is the integer test. Then we print the first call. We see the type of the input. We executed the function. Then second call. And then the same stuff with the float. And we reuse the same value. So the one the one float and the one integer, and the two float and the two integer. And let's see what happens. So on the first call, we pass the integer value 1, we have the Python execution and the graph execution. Okay, this is expected. But on the second call, we have the we pass the integer, the Python integer with value 2, but we have still the Python execution and the graph execution. So we are creating two different graphs, even if the input type is the same. What happens when we move on is that we are executing the float test. We are in the first call of the float test. We pass a float with a value 1, and then we don't have the Python execution, but we have only the graph execution. So we are reusing a graph that we created for the integer types, but for the float execution. And as you can see, the input is a float value, 1.0, but the output is 1. So we lost the correct behavior of the identity function, because this is no more the identity function. Because if my input type is an integer, I want that my output type must be an integer. And if my input type is a float, I want my output type to be a float. And this is completely wrong. This is wrong. But this is how AutoGraph works. Exactly. So this is just no sense. This is completely wrong. But it's a design choice. It's a design choice because this brings us to the third lesson. This is no autoboxing. So tf.function does not automatically convert Python integers to tf tensor with the type tf-int and so on. So there's no autoboxing of Python native type to tf tensor. So when the graph ID, when the input is not a tf tensor object, is built using the variable value. The value. So since in Python this statement down here is correct, we have that one float it's equal to one integer. So this is a design choice. I don't really like it, but this is how AutoGraph works. So this brings us a lot of problems, because okay, we defined the G function that is again the identity. We can start to invoke this function 1000 times and measure the speed. The first time we define it using a tf range. Tf range is the TensorFlow equivalent of the range call, but of course it doesn't produce an integer, but it produces a tf tensor with a type int. And we are executing the function. On the second call we are executing the same code, but with a Python range, so the e-value is are just 1000 different integer values. And as you can see, the time using the tf tensor is less than half a second. When using the Python native types, we are over 5 seconds, just to return the same input. Because of course we are creating 1000 different graphs in the second part, when instead using the first block, we are creating only one graph and using the same graph for 999 times. So this is the lesson. Use tf tensor everywhere. Do not fall back on Python native type. Don't use it. When you are creating a function that uses tf function, just don't invoke this function with Python native types, but use tf tensor. Okay, we can just have a last test. The test is how to check if AutoGraph works correctly when converting Python operators like greater, equal, lesser, and so on. So this function, everyone should agree that all these code blocks should never reach the last end, because of course if we have two numbers, a number can be greater or equal or lesser than another. the else statement, the final else statement, should never be executed. But of course, if you execute this code block passing the same value x, tf constant 1, you execute the function, this is the output. Perfect. So, we have defined a function that returns, that when evaluated, enters in this branch. So, A is greater than B, no. A is equal than B, no. A is lesser than B, no. Okay, so what is it? Amazing. The problem here is that the equal operator is not converted to tf equal. This is a design choice from the TensorFlow 1 version, because internally in the TensorFlow code base they use the Python equal operator to do a lot of indexing using tensors, and therefore they can't use tf equal because of course tf equal produces a tf operation. It's not a boolean. AutoGraph converts the if and the if, but of course it doesn't convert the Python built-in operator correctly. But this is something old, because right now the solution is to use not the Python operators. So it's the same of using the Python types and the tensor types. So you don't have to use the Python operators, but you have to use the TensorFlow operators. So use tf mat greater, tf mat equal, tf mat less. In this way you are defining a graph, and you are helping AutoGraph to correctly define a graph. In this way the function works as we expect. So this is the lesson. Use the TensorFlow operator everywhere and use tf-tensor everywhere. But things are changing, so this is from the day of the release of TensorFlow 2. So on Twitter, Raphael Mendex, sorry for the pronunciation, contacted me saying that, the third part of the articles I wrote on my blog that are the source of this talk now have been fixed. So you can write code in this way, you can write code in this way, and AutoGraph works as we expect. But of course, the lesson still applies, because we want to write correct code that can be graph converted, and therefore using the TensorFlow operators is the correct way to go. So, brief recap. TF variable, so the function that creates a state and needs a special treatment. You have to think about the graph while designing the function, because converting the eager mode to graph mode is not straightforward. There is no boxing over the Python native types, and therefore you have to use tf-tensor everywhere, and it is better to use the TensorFlow operators explicitly everywhere. Okay, so the talk is finished. I just want to share with you this release of the book that covers the function and a lot of the new features of TensorFlow 2.0. And it's been recently released, and you can find a link on my website, and if you want, I have a copy here to show you. So, that's it. Thank you.